New York already built a tunnel around this leak, but using it means shutting down the aqueduct that carries about half the city's water. The new tunnel is lined, dry, and waiting beside the old one. What remains is the moment when water stops moving through the original aqueduct, and workers can connect the bypass at both ends. The problem is no longer how to dig the new tunnel, it is how to turn off the old one without making the rest of the water system less secure. That distinction sounds almost too simple. New York finished the concrete lining inside the bypass in 2021. But lining a tunnel and putting it into service are different milestones. The bypass still has to be joined to structurally sound sections of the existing aqueduct. Until those connections are made, it is a finished path with no water entering or leaving it. The city tried to begin that final phase in 2024. Dry weather changed the operating conditions, and the old aqueduct was returned to service before the bypass connections were completed. As of June 2026, the Department of Environmental Protection says it anticipates restarting the repair work in 2031. Restarting is the important word. It is not a promise that the entire project will be finished that year. So the mystery is not an abandoned tunnel or a failed excavation. It is a working water system that has not yet created another safe chance to make the switch. New York's water supply is much larger than this one repair. Water moves from a network of 19 reservoirs and 3 controlled lakes spread across 3 main source systems. On a typical day, the system delivers about 1 billion gallons to nearly 10 million people in the city and surrounding communities. Most of that journey does not depend on pumps. The department says gravity carries about 97% of the water to homes and businesses. Pumps handle the final stretch for the remaining share. Elevation does much of the work from the watersheds toward the city. Within that larger network, the Delaware Aqueduct normally carries about half of New York City's water. That share is not a fixed number every hour of every season. It does explain why shutting the aqueduct is never just a tunnel decision. When Delaware goes offline, the other parts of the system must cover more demand while crews work below ground. The key is that several sources feed one city. The largest normal path cannot disappear without changing the load on everything around it. The Delaware Aqueduct was driven through rock, and the problem is not a broken pipe lying under a street. Water has been escaping through 2 monitored leak areas in the aqueduct's long underground route. The larger problem is near the Hudson River, where water can move from the pressurized tunnel into fractures in the surrounding rock. The department says those monitored areas can release up to about 35 million gallons a day, depending on flow conditions. That upper bound matters, but it is not a meter reading that stays constant every day. Earlier city documents used lower estimates under different conditions. The careful description is a leak whose rate changes with the amount of water moving through the aqueduct. The city investigated, measured, and planned around that loss for years. Turning the water off long enough to repair the original tunnel directly would have created the same supply problem that exists now. The chosen solution was to give the water a new route around the largest leaking section. That route did not have to replace the whole aqueduct. It had to leave the sound tunnel, curve through new bedrock, and rejoin the sound tunnel on the other side of the leak. In other words, a bypass. The bypass is about 2.5 miles long. It runs roughly 600 feet below the Hudson River, through bedrock, between 2 new shafts built on opposite sides of the river. At that depth and scale, this was a major underground construction job. The core idea was simple: build beside the active aqueduct instead of opening it first. Workers could excavate the new path while water continued through the old one. A tunnel boring machine cut through the rock. Crews then built the concrete lining that would form the finished water passage. The final lining milestone arrived in 2021, years before water could enter the bypass. That separation is what made the construction possible. It is also what creates the problem at the center of this story. A parallel tunnel can be bored, lined, inspected, and left dry without disturbing the live aqueduct. But it remains parallel. It does not become part of the water system by proximity. New York has described the broader Delaware Aqueduct repair program as an effort of roughly $2 billion. That figure covers more than the bored tunnel alone. It reflects the bypass, connection work, shafts, planning, and the other supply projects needed to prepare the system for a long shutdown. The excavation solved the question of where the water could go. It did not solve the question of when the water could be moved there. Picture the old aqueduct as one continuous path carrying water through the leaking zone. The new bypass runs beside that path and around the damaged section. At each end, it approaches a sound part of the original aqueduct. Those meeting points are where the system must change. Workers need to connect the sound upstream section to the bypass entrance. Then, they must connect the bypass exit back to the sound downstream section. After that switch, water can avoid the leaking stretch and travel through the new tunnel instead. The exact geometry is more complex, but the logic is simple. There is no safe way to make those openings while the original aqueduct keeps carrying its normal flow. The live tunnel has to be shut down and drained before the final connection work can proceed. This is why two descriptions that sound contradictory can both be true. The bypass is structurally complete. The bypass is not operationally connected. It can exist beside the system while the water keeps moving. It cannot join the system until that movement stops. Once the old aqueduct is shut, the situation changes in two places at once. Below ground, water must leave the work area so crews can reach the connection points. Across the wider supply system, the Delaware Aqueduct's normal contribution has disappeared. The city still needs water every hour that the repair continues. That creates a clock, but not a simple countdown measured only in construction days. The available window begins with the water already stored in the reservoir system. It changes with rain and snowmelt entering those reservoirs. Daily demand and the amount available from Catskill and Croton change it too. If storage is strong and demand is manageable, the system has more room to operate without Delaware. If dry weather continues and reserves fall, that room narrows. A crew can be ready underground while the supply conditions above ground become less favorable. This is what makes the final connection fundamentally different from the earlier excavation. The bypass could be built beside the live system over years. The connection has to fit inside one protected offline period. Once the old aqueduct is drained and opened, the city needs confidence in the rest of the system. It must carry the load until the new route is ready. Each operating step has its own procedure. But the important dependency is simple. Underground progress needs an above-ground water margin. That margin cannot be delivered on a truck or added to a construction schedule. It has to exist across an entire watershed and supply network. New York entered that operating test in October 2024. The city began the shutdown phase and moved toward the final connection work. At the same time, the region was experiencing exceptionally dry conditions. Reservoir reserves were being asked to support a project window that now looked less secure than it had when the schedule was set. The dry period was not created by the tunnel project. It became the outside condition that changed what the project could safely demand from the water system. New York declared a drought watch on November 2nd. A drought warning followed on November 18th. Those declarations do not mean the city had run out of water. They mark a worsening supply picture and the need for stronger conservation and operating measures. For the aqueduct repair, they also made the remaining margin harder to defend. The department's later account says reservoir reserves were not sufficient to keep the aqueduct offline and complete the project in the spring. It says returning the aqueduct to service protected the long-term water supply. So, the old path was restored and the bypass remained dry. That decision can look strange if the tunnel is treated as an isolated object. A construction project had started. Major pieces were already in place. Crews had prepared for the final work. Why stop? Because the work was happening inside a live utility. Continuing would not have meant betting only on a contractor or a tunnel. It would have meant betting the available water margin against future weather, future demand, and the time still needed underground. The city chose to preserve that margin. The repair window closed before the physical connections were made. New York did not approach the repair with no alternatives. The city had spent years preparing additional capacity and resilience across the Catskill and Croton parts of the system. It pursued upgrades, conservation measures, and other projects designed to make a Delaware shutdown possible. But alternate supply is not a single backup pipe waiting at full capacity. Each source begins with its own reservoirs, inflow, water quality conditions, infrastructure, and operating limits. The amount available from Catskill or Croton can change with the season and with the condition of the system at that moment. Think of the three source systems less like three identical batteries and more like three connected landscapes. Rain may fall unevenly across them. Storage may be stronger in one region than another. Demand keeps drawing from the combined network, while operators adjust which paths carry more water. That flexibility is the reason a long Delaware shutdown can be planned at all. It is not a guarantee that the shutdown works on any date for any length of time. In 2024, the alternatives did not vanish. The available margin around them became too narrow for the remaining repair schedule. A real backup system is valuable precisely because operators do not spend all of its protection at once. Now the shape of the problem is clear. A safe repair window is not a date printed on a construction schedule. It is a temporary condition created by enough stored water, enough alternate capacity, manageable demand, and enough time to finish the physical work. Change one part of that condition, and the window changes with it. Strong reservoir storage can absorb a dry week more comfortably than weak storage. Lower demand can preserve water that higher demand would consume. Faster underground progress matters only if the supply system can stay inside its safe margin for the entire job. Weather does not control a construction plan. It controls how much time the supply system can safely give the work. Construction and operations have to succeed together. The tunnel team needs a dry work area and prepared connections. The water supply team needs confidence that the rest of the network can serve the city while Delaware is unavailable. That is what happened in 2024. The concrete did not fail, and the bypass did not move. The conditions around the final connection changed. That is why drought management became part of tunnel engineering. Dry weather did not damage the new tunnel. It reduced the time and water margin available to put that tunnel into service. Pausing the 2024 work did more than move a date on the calendar. The earlier final connection contract ended, and the department began developing a new contract for the remaining work. Mobilization, planning, and another system-wide shutdown now have to be assembled again around a future repair window. The history is easier to read as a sequence of different milestones. The bypass plan took shape after years of leak investigation. Excavation and lining created the new physical route. The final concrete lining was completed in 2021. The connection phase began in 2024, then stopped as dry conditions weakened the supply margin. In May 2025, the department said it would develop a new contract for the final connections. The city's current planning materials have since moved beyond earlier target years. As of June 2026, the department anticipates restarting the repair work in 2031. That does not mean the bypass will sit unchanged and then automatically open in 2031. It means the city is working toward another attempt at the shutdown and connection phase. The precise completion date depends on work that is not yet restarted. It is tempting to read a long delay as evidence that the engineering failed. Here, the delay tells us something different. Boring the new path was a bounded underground project. Integrating it requires another contract, another operating plan, and another period when the entire supply system can support the switch. The next attempt will need more than a crew and a start date. First, the reservoir system needs sufficient stored water. Storage is the cushion that helps the city absorb the Delaware Aqueduct's absence while daily demand continues. Second, weather and inflow need to support that cushion rather than erode it. No schedule can guarantee favorable weather years in advance. The plan has to account for uncertainty and preserve a way to protect supply if conditions move in the wrong direction. Third, The Catskill and Croton parts of the system need to provide the alternate capacity expected of them. That includes the benefit of upgrades and conservation work developed around the repair program. It does not mean either source becomes an unlimited substitute for Delaware. Fourth, the physical connection and drain-down work must be fully prepared. The city needs the people, contract, equipment, and sequence ready before the old aqueduct gives up its normal role. Finally, all of those pieces have to create enough protected time to finish. A safe opening day is not enough. The system needs a safe window, long enough for the connection work and the return of water through the new route. No one can responsibly predict the weather in 2031 from here. What the current schedule tells us is the scale of coordination still required before New York tries again. The Delaware bypass is an engineering accomplishment. Workers created a new route through bedrock below the Hudson, while the old aqueduct kept serving the city. The fact that the bypass remains dry does not erase that achievement, and it does not make the tunnel useless. It does reveal where the harder boundary was hiding. Construction could happen beside the live system. Integration has to happen inside it. The final step touches reservoirs, weather, daily demand, alternate supplies, contracts, crews, and the time available to bring them together. We tend to picture infrastructure as individual objects, a dam, a pipe, a tunnel, a treatment plant. But those objects become useful through relationships. Water stored upstate has to meet a route, an operating decision, and a person opening a tap many miles away. The bypass is waiting for one more relationship to become possible. The rest of the system must create a safe moment when the old path can stop and the new path can take its place. That coordinated moment is as much a piece of infrastructure as the concrete tunnel itself. New York built what it could while the water kept moving. The bypass now waits beside an aqueduct that still carries about half the city's normal supply. The part that remains begins when that movement stops. The old aqueduct must be shut and drained, the connections must be made, and the wider system must keep serving the city until water can enter the new route. New York built the physical solution. Using it depends on something less visible: enough water, alternate capacity, and time for a safe switch. Until then, one tunnel carries the water, the other waits in the dark.